This is example 8.4. I did not update my thing, sorry. From Discovering Design with Chemistry. A chemist burns 50 grams of an unknown substance containing only carbon and hydrogen in a combustion analysis experiment. That means we have carbon and hydrogen in some unknown ratio, and we're combining that with some oxygen. She collects 146.4 grams of carbon dioxide and 89.9 grams of water. So we know what it produces, CO2 and H2O. And they even tell us how much we get of each of these. We get 146.4 grams of this one, and we have 89.9 grams of this one. And then they want to know what is the empirical formula of the substance. In other words, what do we put where those little question marks are? This one might sound a little bit confusing, so we're going to use what we've been learning to figure it out. So let's start by alright, so let's find these two and turn them into moles. How many moles do we use of carbon dioxide and how many moles do we use of oxygen? That means we're going to need to find all those things on the periodic table. So here's our carbon, our oxygen, and our hydrogen. We know how to find a conversion relationship and then how to use it. So for carbon dioxide, we have 12.01 plus 2 times 16.00, and that will give us how many grams is in 1 mole, so that we can figure out how many moles of carbon dioxide we need, or that we used. And then, let me get a new color here. And then for the water, we have 1.01 times 2, because there's 2 atoms of that, plus 16.00. And that will tell us how many grams is in 1 mole of water. Alright, so let's move that periodic table to the side. Alright, so let's do carbon dioxide first. So 12.01. You can't even see what I'm typing. Plus 2 times 16. So we have 44.01 AMU. Or in other words, 1 mole of carbon dioxide is 44.01 grams. Okay? Now let's do our water. Oh, you know what? I could probably do this one in my head, but I've already pulled up the calculator, so we'll type it in. Alright, so we have 18.02. And so that tells us that 1 mole of water is 18.02 grams. Alright, so using those two, we can figure out how many moles we have of carbon dioxide and how many moles we have of water. So they told us that we had 146.4 grams of carbon dioxide. Again, I'm using my colors like I did in previous examples, so I don't have to keep writing all the stuff all over again. Alright, so 1 mole is 44.01 grams. This is my, use a different color to box it in. This is my conversion relationship box. (146.4) divided by 44.01. Those both have 4 significant figures in them, and so we're going to keep 4 significant figures, so 3.327. That's the moles of carbon dioxide that we used. Alright, so now let's do the water. So for the water, we had 89.9 grams, and we want to know how much water we had. So now we're working with this one. right? So 1 mole of water is 18.02 grams. And this one's going to be limited to 3 significant figures because of the, let's pay attention to what I'm doing. Because of the 89.9, we get 3 significant figures. So the 8 that comes after this is going to round that up. So it'll be 4.99. All right, so if we have 4.99 moles of H2O, that means we have 4.99 moles of the H2 and 4.99 moles of the O. When I was first reading this, I remember being confused about that concept. So think of the H2O like a fruit basket. I have little pairs of bananas and individual apples. And so if I have a dozen fruit baskets, I have a dozen pairs of bananas and a dozen individual apples. I hope that makes sense a little bit. Okay, so I dropped my pen. All right, so let's go back to what we were looking at over here. When we first did, we sort of set it up so that we could look at things. We have carbon and hydrogen as our unknown substance. So the carbon has to come from the carbon dioxide and the hydrogen has to come from the water. And then of course the oxygen was just in the burning need for the fuel. So we're not going to really worry about that right now. Because I want to think of the hydrogen as individual atoms in this mystery CH that we're trying to make, I want us to recognize that we have 4.99 moles of H2 and we have 3.327 moles of carbon. We also have 3.327 moles of O2 and 4.99 moles of just O, but we don't care about those. So this is helpful to know. And then down here, we want to just know how many moles we have of just hydrogen, not of H2, because we want to know how many we have. So if we have, think about this, if we're going to round numbers to make this easy to think about. If we had 5 pairs of bananas, how many total bananas do we have? We would have 10 bananas, right? And so if we're only wanting 1 hydrogen and not pairs of hydrogen, then we have to double that number. So it needs to be 4.99 times 2 to get that. And so that is 9.98. All right, so this is how many moles we have of hydrogen at the end, and this is how many moles we have of carbon at the end. And so we should still have these numbers at the beginning. So what we're going to do is we're going to figure out what the ratio is between the carbon and the hydrogen so that we can figure out its empirical formula. When we do a ratio, if you want to end up with a number that's not a fraction, you need to put the smaller, number on the bottom. So we're going to put 3.327 on the bottom, and that's our moles of C. And we're going to put our 9.98 on the top, and that's our moles of H. And so when we divide those, we can think of it as like having 1 C for every however many H's. So 9.98 divided by 3.327. Now we have to have only 3 significant digits, and when we round this to only 3 significant digits, it becomes 3.00. So there are 3 hydrogen atoms for every 1 carbon atom in the thing. So we can now make our formula. So for every 1 carbon atom, there are 3 hydrogen atoms. And of course, we don't actually write the 1. So this is our empirical formula, CH3. I'm going to back that up so you can kind of see the whole process in case you want to.